ahead and do that. Hold on.
All right, a proof is an argument that uses logic, definitions, properties, and previously proven statements to show that a conclusion is true. So if we're using those things, are we using inductive or deductive reasoning in proofs? Deductive reasoning. So when we explore something, we use inductive. When we're proving it, we need to use deductive reasoning to prove it. We can kind of figure it out for ourselves or convince other people with an inductive exploration or inductive examples, but that's not a formal proof. So the justifications are given to show every step is valid. So we have a couple things. We've talked about them from the beginning here. Theorems versus postulates. Euclid gave us our first 5 postulates, things that we could assume to be true, because there is no formal way to prove them. These are things that are assumed to be true without proof. Not because Euclid felt lazy, but because there was, like, especially with our undefined terms of point, line, and plane, there was nothing that we could really prove those things with other than to look at a million examples and everyone agree that this holds true. But based on some of those things, we were able to prove other statements that we wanted to make. So theorems are usually conditional sentences, but not always. So if-then statements. I'm just going to put statements that we can prove with deductive reasoning. They're not necessarily assumed to be true. Now, because you did a ton with geometry in middle school, some of these things you're like, well, I know that. You know that because you explored it and you understood it inductively. Like, you got it, that it was always going to work. But that wasn't really a proof. And so some of the things you're like, well, I already know that. Yes, but we're going to prove them. And that way we verified that using deductive reasoning, we get the same conclusions. So what's in common with these is that both are used in writing proofs. They're also both usually written as conditionals, but not always. So the most important part is, though, that they're both used in writing proofs. So the thing is, if we've proven a theorem, then we can use it to prove other theorems. So the most basic ones in geometry are the vertical angles theorem, which you guys already know the fact that vertical angles are equal, but it's not really a fact, it's something we have to prove. We can't just say, oh, they always look like it. We have to be able to prove it deductively. And there's something called the linear pair theorem, which says linear pairs will always be supplementary. Those are used throughout the entire course. So we're going to be proving those, if not today, then tomorrow. Also in our proofs, we're going to be making some statements about things being equal versus things being congruent. When we're trying to build equations, the really cool part about geometry is sometimes we can build equations to do proofs so that we can get a system of equations to help connect different things that are in a picture. So sometimes we'll want to have things be equal, and then sometimes we'll just want to make a statement that certain things are congruent. So we have the following properties, and you kind of previewed these when you did your algebraic proofs, and we're looking up some things in the book. But we have reflexive property of equality. That's where you say maybe the measure of angle A equals the measure of angle A. And you're like, well, what's the point of that? Well, if you have a picture where two triangles or two shapes share angle A, and you're trying to show that all the different angles are congruent, this can be a helpful statement. So it's kind of like a mirror reflecting the exact same thing on the other side of the equals. The equals is like a mirror. Whereas if we were doing property of congruence and we wanted to talk about angle A, but we didn't want to say, we weren't building equations, then we would say angle A is congruent to angle A. This can also happen with sides. We can do this with segment lengths. Maybe we want to show the segment, two parts of a midpoint are equal, or something like that, so we say their measures are equal, or maybe we're trying to get a congruent statement, so we say, hey, these are congruent. But that wouldn't be from midpoint, it would be from something else, so if we knew that they were the same exact segment. Symmetric property of equality. This is sort of a little more like a reflection, but this is the same thing reflected across. This is kind of like the law of, no, it's not. Hold on. A equals B, so B equals A. It's kind of like the commutative property, right? For addition and multiplication, it doesn't matter what order it's in, it says the same thing. So symmetric is where it's the same thing, just the reverse order. So symmetric, same thing. So over here I might have side AB is congruent to side BC, but then instead I say BC is congruent to AB. Really, I'm saying the exact same thing, it's just in a different order. By the way, this is most commonly used when we solve an equation and we're doing this in a proof, which you did some earlier, but I didn't make you finish all the way to plugging stuff back in. But let's say I had a number. Let's say we had a 5 equals x. If I told you to solve an equation, would you go and say 5 equals x? What would you say? So that's where this is the most commonly used. You solve the equation, but your variable's on the right-hand side. Well, how can you justify switching it around? Symmetric property of equality. Transitive property is a lot like the law of syllogism, but I say it is like a train. You have an engine, you have a connecting car, and you have a caboose. So we have the statement like A equals B and B equals C. So A equals C, just like the law of syllogism, right? Here's the engine, here's the caboose, here's the connector. We get from start to finish. When we're talking about congruence, maybe it's that angle A is congruent to angle B, and angle B is congruent to angle C. So angle A is congruent to angle C, and that would be transitive property of congruence. We're going to be using these properties a lot in proofs. Maybe not as much. In this unit we'll use it a little bit, and the next unit we'll use it a lot more, and then next semester we'll use it a ton when we do congruent triangle proofs. So we're really lazy, right? We don't like to write out the words property of equality, right? So if you're abbreviating, this one would be reflexive, and if you put that, I'll be okay with it. You should probably spell out reflexive, but I'll be okay with that. P-O-E. Symmetric, P-O-E for property of equality. We still read it as property of equality.
Wait, isn't it property of congruent?
Nope, these ones are property of equality.
Oh.
This one is transitive, and we will write that one out. Property of equality, we use that one quite a bit. Now, on the other side, it's the same things, but it's property of congruence. So I don't want you going around saying reflexive POC, symmetric POC, transitive. Still say property of equality, just like you say I live in Commerce, Michigan, even though we abbreviate it MI. But you can abbreviate it so you don't have to write out the words property of congruence. I'd like you to take a moment using these to try to justify statements A through H. Identify which property is being used. All right, normally I'd call on you randomly, but we're kind of pressed for time with getting our proofs in too. So is this one, you can shout it out, property of congruency or property of equality? Congruency. Which one is it? Reflexive. What about this one, property of congruence or property of equality? And since it's switched order, it is symmetric. Who thinks they know the next one? Go, Ashley. Transitive property of congruence is correct. The next one is easy. It's also a property of equality. What's the word in front? Reflexive. Who thinks they know letter E? Go for it, Blake.
Symmetric property of equality.
Symmetric property of equality, correct. The next one is also reflexive property of equality. Who thinks they know letter G? Go for it, Kevin. Transitive property of equality is correct. It's going to look different in the proof when we see it. You're going to see these two as separate lines in the proof, and then you'll make this statement as your next line, and then you'll have transitive property. All right, and this next one, who has the last one for us? Robbie.
I got symmetric property of equality.
Symmetric property of equality is almost. Property of congruence. Pay careful attention to the symbol in between. Okay. All right. So we will use some of these in our proofs, just not right away because we're still building off of some of the vocab from the first unit. So applications of definition of congruent angles. What does it mean for angles to be congruent?
They're equal.
All right. So I have a statement here. Angle A and angle B are congruent. That is what's given to me. So I put that as my first line of my proof. And you just said, what does it mean to be congruent?
They're equal.
So what's equal?
The angles.
The angles are equal?
Angle measure.
The measure of the angles, thank you. Measure of angle A equals the measure of angle B is the exact line that comes from the fact that they're congruent. And the reason, anybody have an idea of what we'd put for the reason? Well, how did I know that their measures are equal? Perfect. Definition of what? Of congruent. Perfect. Definition of congruent. We also have these expressions, which I'm going to also consider to be given, and I'm just not going to write them in. So now I can substitute in for measure of angle A, the 35, and substitute in for measure of angle B, the 3x minus 5. And so we've done these proofs before. That is substitution. And from here, there's two properties I'm going to use to get my final answer. Anyone know what the last two properties are going to be? Just looking at the equation. Addition property of equality and division property of equality. Absolutely. So we're going to add 5 and we're going to divide by 3. Now, you're welcome to show those algebra steps. In fact, I'd encourage you to. We're more likely to make errors when we don't show our work. But we don't label those as lines in the proofs. We just kind of do the work in between or off to the side. Questions on that proof? Yes? POC is P. There is no S. Okay, postulate. Postulates and theorems. We haven't done theorems yet. We only have postulates so far. We're going to be building some theorems tomorrow. All right. Angle C and angle D are complementary. So we're going to put all of this, except for the proof part, as our line 1, just so that we don't have to keep writing given over and over again. In some of the fill-in-the-blank proofs that you will have later, they will spread the givens out throughout the proof. You'll be like, where did this random statement come from? And you'll look back and realize that it was in the given. So they might have the measure angle C and measure angle D expressions written down here somewhere. So if that's given, what key vocabulary word do we have in this? Complementary. So we're going to say, what does that mean about the measures of angle C and the measure of angle D?
They are equal.
They're going to add up to 90 degrees by the definition of complementary. Now the good news is, other than angle addition postulate and segment addition postulate, so far everything else is a definition. But we're going to have some theorems soon, so that's going to change. Now I just plug in the expressions 3x and 2x plus 30 using substitution. What will my next justification be? Anybody know? Oh, by the way, I forgot to write the equals 90. That's kind of important.
subtraction.
Nope. CLT, yep. Exactly. And there are two more justifications that are going to happen in this proof. Raise your hand if you know what they are. Two more justifications that are going to happen in this proof. This is an algebra proof, so we're pretty familiar with these. Two more things that are going to happen that we're going to justify. Anybody know? Only two
Subtraction.
people. Go for it. Subtraction property of equality and division property of equality. Absolutely. So I'm going to subtract 30 from both sides, giving me 5x equals 60. I'm going to divide by 5, giving me x equals 12. Now, we were supposed to prove the measure of angle C. So I do need another line in my proof. It's not going to fit. I'm going to come up here because I'm going to skip the supplementary example other than to make sure you know how to set it up. So line 7 here would be the measure of angle C, which is what I'm supposed to find, equals 3 times 12. Which is equal to 36 degrees. What did I just do? Substitution. Good. I don't want you to do the full thing for this problem because we don't have time. We've got to move on to the other things just to review them. I just want you to set up what two lines come after the given. So our given is all of this wonderful stuff right here except for the prove statement. I want to know what your next statement would be based on key things in that given information and what your step following that would be. We're not going to do the whole thing. I just want you to set it up because that's the most important part. That's the geometry part. So take a moment to set those up. So who's pretty confident they have the first line after the given correct? Blake.
So I did measure of angle T plus the measure of angle V equals 180. I said that was the definition of supplementary.
Perfect. Definition of supplementary. Angle measure of T plus measure of V equals 180. Because that was the given information. You saw that key word that they're supplementary. Now you can build an equation. If it helps you for this, it's going to help us. And then the next line. Who has the next line? Go for it.
It's substitution, so I put 3y plus 2y plus 80
3y plus 2y plus 80 equals 180. Perfect. And then we would just combine like terms and solve from there. Any questions on setting these ones up? They should be familiar because we didn't do this with complementary and supplementary, but we did similar proofs. And we're about to review some of those. So we see this picture, and right now you know you're going to use the angle addition postulate because it's telling you that, but they're not going to tell you that. They're just going to say use the given information to write a proof. And so they might even say something about these being adjacent angles. They might not. Basically all the information in the picture is given. Now, did they tell me that BD was an angle bisector?
No.
No. If they did, then I would use the definition of angle bisector to set the measures of the angles equal and then plug in the expressions. They didn't tell us that. They did tell us the whole thing is 88 degrees. So if you guys were just solving this on the last BA, what would you do with these expressions?
Combine them.
Combine them and make them add up to 88. Now, in the proof, we can't just start adding expressions because they don't know where the expressions came from. We need to say that we are really adding angle ABD and DBC, the measure of those angles, and that those are adding up to the whole angle ABC. Because the angles are adjacent, and it's given in the picture that they're adjacent, otherwise they'd have to tell you that. So, what am I using? These two angles add up to a bigger angle. Angle addition postulate. It's one of the only two postulates we have so far. There will be many more to come. So now, excuse me, I put 88 degrees. I wasn't supposed to know that. I was supposed to know that the whole thing is 8x. So now I can plug in my expressions, 3x plus 5 plus 6x minus 16 equals 8x. And that's substitution. Any questions on those steps? What's my next reason going to be? Combine like terms and solving from there. If I had more time, I would do it right now, but I want to make sure we get through how to set the last two up. Even though it's review, some of you need the refresher, and when you're first starting this, you had a lot thrown at you at once. All right, in this problem, they only give me, wow, that's really hard to see. That's 4x minus 4 up there for the whole thing. They're going to tell me that, they'll probably tell me either use the picture to set up a proof, or they'll say M is between N and O. You saw problems like that, you knew how to set up your equation. Since we're doing a proof though, we can't just build the equation, we have to build it with the segments or angles first. So what segments am I going to put together? NM plus MO equals what? NO, and that's actually correct. So this piece plus this piece adds up to the whole thing. If we're doing that with segments, just like angles, this one's going to be the segment addition postulate. From there, we plug in the expressions. 2x plus 3x minus 9 equals 4x minus 4. And that is substitution. And from there, it's another algebra proof, combining like terms, getting your variable to one side through subtraction property of equality, and so on. There's more to this, I'm just skipping it because I know you guys can do the algebra part. Our last one, again, it's going to tell you right here, and you can look back at your notes for now, but you want to be able to do them without looking back. I see this key vocabulary word in the given information. And so I know that at some point that I'm going to use the definition of midpoint. And for us, since we're so early on in this, it's going to be pretty much the first step, but it won't always be the first step. So I'm going to use the fact, I might even draw a picture to help me see the problem. ED is 4x plus 6. DF is 7x minus 9. Because it's the midpoint, I know these two pieces are equal. So I'm going to say, technically I'm supposed to say this, ED is congruent to DF. If you say is equal, I will give you credit. But technically the definition of midpoint is that they're congruent. Because they're congruent, I can say that ED equals DF. Raise your hand if you know the reason why.
Because ED is like the measure of line segment ED.
D, yeah. See this right here? What does that mean? Equal in measure, and that's the measurement. So what would the reason be? Definition of congruent, absolutely. So just like, hey, we knew midpoint, so our next line is definition of midpoint. Now I know congruent, so my next line is definition of congruent. Now, I don't like writing this step out every time. That's why when I first modeled these for you, I did this with this line, and if you do that, I will accept it. But I just want you to know that technically, you're supposed to go from congruent to equals by definition of congruent. So now I'm going to plug stuff in, and when I plug stuff in, my reason is, and from there you've got the rest of the proof. You can combine like terms. Actually, there are no like terms to combine. Subtract, and divide, and you've got your answer. So that concludes the examples for today. We're actually going to be doing some real proofs tomorrow in geometry, but I got to make sure we're solid on this. So you're going to get a little bit of practice with these